Hello everyone and welcome to Module 2. This is the first of two lectures where we'll talk about the foundations of inferential statistics. To give you an overview of Modules 2 through 3, in Module 2 we'll talk about the foundations of inferential statistics and specifically cover probability and sampling distributions, specifically the normal distribution. And we'll also talk about making inferences and estimates, the basics of what inferential statistics do. In Module 3, we'll take that information and apply it to understanding hypothesis testing. We'll cover significance testing. We'll also cover the distinctions between statistical and clinical or practical significance. We'll cover effect size and power, and we'll also talk about choosing the appropriate statistical tests. I'll say this several times throughout the course of the semester. Take a deep breath. For those of you who feel intimidated by math and by some of the mathematical concepts underlying statistics, we'll cover a lot of those mathematical concepts in Module 2. These are intended to give you a conceptual understanding of inferential statistics, not to actually prepare you or give you the skills to actually do all of this math. So try and follow along with the ideas. I'll go through, and I have a lot of text on some of these slides, so feel free to pause. I would say probably read the chapters in the book prior to watching this lecture, and hopefully between the two we'll be able to give you a solid foundation of the basics of inferential statistics. So first, what are statistics? Statistics are mathematical tools used to organize, summarize, and manipulate data. And there are two primary statistical applications. The first, descriptive statistics, which you covered as well in 850. In descriptive statistics, we use these to describe or summarize individual variables, univariate statistics, or associations between variables, bivariate or multivariate statistics. In inferential statistics, we use statistics to make an inference about the characteristics of a population based on data from a sample of that population. And inferential statistics are essential tools for hypothesis testing. So a reword of a question that we might ask in hypothesis testing would be, how likely would it be to obtain a difference at least as large as that we observed between groups in the sample if in fact there is no difference between groups in the population? So again, making inferences about a population based on samples. And the basic logic underlying this is that the populations we wish to study are almost always so large that we're unable to gather information from every case. So if our population of interest is adolescent girls, for example, there's no possible way we could survey every adolescent girl in the country or in the world. And so the solution to this is that we choose a sample. This is a carefully chosen subset of the population, and we use that information gathered from the cases in the sample to generalize to the population, to make population level estimates. And the statistics that we talk about are mathematical characteristics of samples. Parameters are mathematical characteristics of populations. So we may say the sample mean, and that would be the statistic, whereas if we would say the population mean, that's a parameter that we are estimating. And so we use statistics to estimate parameters. And hopefully this will make more sense as we move forward in modules 2 and 3. So how do we use those sample statistics to make inferences about a population? So some of the basics of this is central limit theorem. So according to central limit theorem, the sampling distribution of sample means selected from that population will be normally distributed. So even if a particular variable isn't actually normally distributed in the population, if you take enough samples from that population, those sample means will be normally distributed. So in other words, we can boil this down and say that most variables are normally distributed, especially with large enough samples. And so knowing that a variable or variables are normally distributed, and knowing what we know about the basic principles of probability, which are covered in your book and we'll talk a bit more about in this module lecture, we can make population level estimates or parameter estimates from sample statistics, and we can also determine how confident we are in those estimates. And we do that by using the sampling distribution to make inferences. So a major objective of statistical inference and sampling theory is to provide estimates of unknown population parameters from sample statistics that can be easily obtained and calculated. So again, we can't ever actually know the population mean because we can't ask every single person in the population. And so we have to estimate that population mean from a sample statistic that we can actually obtain and calculate. And so what we know, what your book, I think what your books demonstrate nicely is that we will always get a sample statistic that it's not exactly the population statistic. So we will always get a sample mean, for example, that's not exactly the population mean. And that's called sampling error. It's not an error in our technique, but just the nature of samples and sampling. So the question that stems from knowing about that sampling error is if sample estimates vary, and if most estimates result in some sort of sampling error, how much confidence can we place in these estimates? So in other words, on what basis can we infer from the sample to the population? And the answer to this question is to use the sampling distribution, which is a theoretical probability distribution of all possible sample values for the statistic in which we're interested in. So the theoretical sampling distribution helps us to estimate the likelihood of the sample statistic that we actually got, which enables us to generalize from the sample to the population. And the sampling distribution, your book reviews this. This is a distribution of a statistic for all possible samples of a given size. And the sampling distribution is a theoretical concept, so we don't actually do what it takes to generate a sampling distribution. But we use the information from the sample, and we link that information from the sample to the population via our knowledge of this sampling distribution. And again, according to the central limit theorem, if all possible random samples of a particular size are drawn from a population, as that sample size becomes larger, the sampling distribution of sample means becomes approximately normal. So again, this is this basic idea that we know is true in the world, that most variables tend to be normally distributed, particularly if you're looking at the sample mean of a sampling distribution. And so these are the means of a number of samples drawn from the same population. And this is unfortunately one of those things that that we just have to say. Somebody at some point said, you have to trust me on this. Obviously, mathematically, that was demonstrated to be true. And this is one of those things now that is a basic of statistical tests. We have to say this is something that we assume to usually be true. And many statistical tests make this assumption that the data approximate a normal distribution, meaning the math and logic underlying the statistical inferences and tests that we conduct are based on this theoretical normal sampling distribution. And there are a variety of other tests that are based on other kinds of distributions, like a Poisson distribution, binomial models, etc. Those are largely outside of the scope of this course, though we'll talk about some of those at the end of the semester. But for now, we're going to talk mostly about statistical tests and inferences that assume a normal distribution. So what does this normal distribution look like? The normal curve is bell-shaped. It's unimodal, meaning there's a single mode. It is symmetrical, so it's the same on both sides. It is unskewed, which we'll talk a bit more about that, so there are not more cases on one side than the other. And the mode, the median, and the mean are all the same value. And so the distances on the horizontal axis always cut off the same area. So the space between this part, the middle of this distribution, and over here is the same as the space between here and over here. And so we can use this property to describe areas above or below any point in this distribution. And I'll demonstrate this in a moment. So what we know about the normal curve, this theoretical normal curve, is that when we're talking about a distribution of scores out in the world, we know that roughly 68% of scores typically fall between one standard deviation below and above the mean. About 95% of scores fall within 2 standard deviations above and below the mean, and 99% of scores fall within standard deviations of 3 standard deviations above or below the mean. And so z-scores are a way to help us standardize scores to be able to represent a score's location in its distribution of scores. And this allows us to compare distributions of a variety of scores that may be scored on different metrics. So their means are different, they mean different things, but turning them into z-scores allows us to be able to represent a score's location in its distribution of scores using a standard metric. And this formula changes a raw score into a standardized score. And so when we talk about finding an area under the normal curve, we first have to compute this z-score, which is an individual score minus the sample mean divided by the standard deviation. And so we can also use Appendix B, and it's Table B1 in your Salkind book, to find the area between the mean and the z-score. So Appendix B has two repeating columns. You can look at Appendix B in your book, and your chapter also talks, Chapter 8 also talks about looking at this table, and we'll lead you through that as well. But the two columns in Appendix B, Table B1, are the z-score column and the area between the z-score and the mean. So let's say we want to use Table B1, Appendix B, to find out the area between the mean and the individual z-score that we're looking at. So let's say we have an individual score, we've turned that into a z-score, and we want to see what the area between the mean and the z-score is. So we'll find our z-score in this z-score column, and we'll look to the right to find the area between the mean and the z-score. So let's say we're looking at a z-score of 1.67. And so the area between the z-score of 1.67 and the mean is 45.25. This is expressed as a percentage. In some tables, you'll see 0.4525, but in the table in the Salkind book, this is expressed as a percentage. And because we know, again, based on this normal distribution, that 50% of scores fall above and 50% of scores fall below the midpoint, this mean point, on the normal distribution, we can add together 50 and the area between the z-score and the mean, which tells us that 95.25% of scores fall below a z-score of 1.67. And so what this tells us is that there is a 4.75% likelihood that any score will be this score or above. So the probability of getting this score is less than 0.05. And this connection here between the likelihood of getting this score and the probability of getting the score, which is the same thing, will make a lot more sense when we start talking about the individual statistical test, which typically use p-values or probability values to tell us whether or not something is statistically significant. And we'll talk more about that, and hopefully that makes more sense. But in this particular example, if we go back to our picture of this table, we can say, for example, I think I have a picture of this actually. We can say, for example, if we have a z-score of 1.67 over here, and we want to look at the distance, the area between the mean and the z-score. So at a z-score of 1.67, that is 45.25%. And then we know that the distance between this mean and the other side of the curve is 50. So we add together this 50 and this 45.25, and that's how we come up with this 95.25% value. So we know that in a distribution, in a typical normal distribution, whatever score that we utilized to give us a z-score of 1.67 actually corresponds to a point in the distribution. And so then if we go back to that and then subtract 95.25 from 100. There's always 100% of scores under this normal curve. So if we take 100% of scores minus this area that's below this point or below that score, what we get again is 4.75. And that tells us that there is a 4.75% probability that the score of getting this score. So the probability is less than 0.05. And hopefully that will start to make more sense as we connect this to p-values as we move forward. So using what we know about probability and the normal distribution and sampling distributions, because we know how likely a given score is, so the probability of a given score based on a distribution of scores, we can utilize specific statistical tests based on those standard likelihoods to determine whether the observed score, and that could be a mean, a variance score, a correlation, etc., is a score that we'd find by chance. That's typically our null hypothesis, that there's no difference, or that this score is not different from the population, or if that score is unusual in some way, so based on some relationship, treatments, some other variable, and this is typically our research hypothesis. And we'll talk more about hypothesis testing in Module 3, and so this will make a bit more sense then. And again, what we're typically doing is trying to estimate population level parameters. So utilizing what we know about probability, the normal distribution, and sampling distributions, we often make both point and interval estimates. Your Huck book talks about this distinction. Interval estimates are typically things like confidence intervals, margin of error, as it's otherwise known. And so knowing what we know about these theoretical mathematical ideas, we can use that information to make point and interval estimates of population parameters using the sample statistics. So based on the normal distribution and the associated standardized scores, or z-scores, that go along with that normal distribution, we know that 68% of all random sample means will fall within plus or minus 1 standard error of the true population mean. And so let's take an example here. Let's say we have a sample mean of 7.5. This is actually from general social survey data of the number of hours worked per day. So on average in this sample, people worked 7.5 hours per day. And there was a standard deviation of 1.5. And this was from a sample size of 500 people. So we could then calculate an interval estimate, or a confidence interval, using the formula for confidence intervals, which is the individual score plus or minus the z-score multiplied by the standard error of that score. And so first we have to calculate the standard error. And the formula for standard error is the standard deviation divided by the square root of the sample size. So 1.5 divided by the square root of 500 gives us a standard error of 0.07. So we would put 0.07 in the parentheses right here. Then we would use the formula above to calculate the 95% confidence interval. So first we would have to look up the z-score. So if we have an individual score of 7.5, we would use the formula that we talked about before to calculate the z-score. And the z-score that we get is 1.96. And so we take this individual score plus or minus 1.96 times 0.07. And so what that gives us is a confidence interval of 7.36 to 7.64. And we can interpret that by saying that we are 95% certain that this interval captures the population parameter. In other words, if we collected many samples of 500 people from the population, 95 times out of 100, the true population mean would be included within our computed interval. And we also utilize this information to conduct hypothesis testing, which we'll talk about more in Module 3. But I want you to understand the basic ideas of creating these parameter estimates. So while it may seem like understanding normal distributions and the basics of probability is perhaps unrelated to conducting a t-test, for example, to look at the difference between two groups, we utilize all of this mathematical information to create the mathematical formulas and underlying math for all of our statistical analyses. And so this gives you a sense, hopefully, of how we do that. So in summary, some of the conceptual pieces that it's important to know are that statistical analyses use our theoretical understandings of how probability distributions typically work to make inferences about populations based on sample statistics. As educated researchers, we often have, hopefully, educated guesses, which we call hypotheses, about what we think is the truth in the world, what we think is actually happening in populations. And so in Module 3, we'll extend these ideas of probability and normality to conduct hypothesis testing and interpret the results of our hypothesis tests. And that's what we'll do for pretty much the remainder of the semester. But we'll talk in Module 3 about the basic ideas of hypothesis testing. So hopefully between reading the chapters in the book and watching this lecture, you'll have a better sense of the basics of inferential statistics. If you have questions, comments, post those under the general discussion forum on the message board, and I'll try and clear up any misunderstandings, answer any questions, and if there are patterns of questions, I'll try and deal with those in the lecture for Module 4. Before I close out, I will talk a little bit about the Module 2 assignment. So for the Module 2 assignment, you'll turn in your variable selection worksheet. And to do this, you should explore the AdHealth dataset. It's in shared files, and I linked into the course content for Module 2. And you'll select anywhere between 5 and 10 variables of interest. You may select 5 to 15. This maximum number is not a hard and fast rule. I would say you're going to want at least 5 variables that you're interested in, but you may have closer to 15 or so, and you won't be tied to any of these variables. So if you start creating a research question, going down a path that's interesting to you, and you find another variable that you want to pull in eventually, that's fine. You'll be getting rid of many of these variables as you refine your research question. But as you select these variables, they should be variables that you think might be related to one another, so that you can use these variables to develop a research question that you'll answer conducting analyses of these data. So under the Assignments tab, you'll turn in this worksheet. The worksheet's provided to you as well as an example of how to fill in that worksheet. And if you have specific questions or comments about completing this particular assignment, you can post that under the variable selection worksheet topic in the assignments forum. So again, questions about the module content, the basic ideas that we cover, post under general discussion forum, and questions about the specific assignment, post those under the variable selection worksheet topic. And we'll pick up in Module 3 and try and take these ideas and apply them to understanding hypothesis testing.